So, good afternoon, and today's topic is actually quite straightforward. I'll try to explain you how airplanes fly. Okay? So, how do airplanes fly? I have a few ideas. You have an idea? Yes, please.
There is a motor pushing the airplane forward.
Yeah.
And there is the wings are changing its shape to when the air is going to these wings, it's making it up. It's flying.
Okay. Not so sure. Yes.
Changing pressure, difference in pressure.
There's pressure and difference, but why does the pressure difference come? A lot of people say there's a pressure difference between the upper surface of the wing and the lower surface of the wing. There's more pressure in the bottom, therefore the airplane will go up. The question is, why is there more pressure underneath the wing?
Speed of air changes.
The speed of air changes. Some people say it is faster on the top, slower on the bottom. Why would that be?
It starts on top, so it wants to go with bottom.
Yeah, they try to meet at the end, but why would they want to meet at the end?
Physics.
Physics, but why? Yeah, there must be a simple explanation.
Because of airfoil.
Yeah, the airfoil is probably has a certain shape, but there's a little bit more fundamental, something more fundamental to it, why airplanes fly, okay? Sometimes I want to be able to explain this to my mother. My mother asked me, how do airplanes fly? I should have a simple answer, right? The answer is actually quite straightforward, and this is what I want to try to explain it to you now. Do you know these things? They're like water jets. Have you seen them? There's a little pump here, and you have this huge water. It sucks the water and pushes it back in, right? So when you push down water, you go up. Is that something surprising? Not really, right? I mean, everybody kind of understands that if you push water, you would go up, right? Newton explained this with the third law of motion. For every action, there's a reaction. So if you push something, it will kind of push you back. If I push this chair, I will push myself up, right? That's kind of obvious. It's the same thing. You throw something, you'll push yourself up, right? You can also explain this from conservation of momentum. Right? The momentum is conserved. So you're pushing something this way, it will keep you up. I think this is quite intuitive for most people. Right? So let's look at this. How do you think the helicopter is staying up in the air? It does a very similar thing. The rotors are turning at the top and they're pushing down air so that the helicopter stays up in the air. Very similar concept. It's not very different from this. Here it's pushing down water. Here it's pushing down air. Okay? So you push down air and you stay up. Conceptually it is very similar, isn't it? How do you think birds fly? With their wings. They do a similar thing. They take a lot of air, push it downward, and keep themselves up. So you need to push something downwards to keep yourself up. Yes?
And how does the helicopter push the air?
That's a good question. How does the helicopter push down air? We know you can see it in the picture, there's air being pushed down, right? And if you stay underneath the helicopter, you will feel a lot of air coming down. We call it the downwash. How does it do it? Well, it's not very straightforward, but the blades, they are at a certain angle. So if they rotate, they take the air and try to push it downwards. Actually, this question will be clearer in a minute when I start explaining. I will come back to this, okay? So the birds, they push down air. So how does the airplane push down air? I mean, there must be something be pushed down, otherwise you cannot stay up. You need to push down something to stay up, okay? So if you look at an airplane, it doesn't seem to be doing this with the wings, right? And it's not turning or not blowing air downwards, but it is doing something with the air. It's actually the same concept. An airplane also does a similar thing with the wings. It tries to push down air by staying up. So here's what happens in an airplane. When it flies forward, right, relative to the airplane, the air moves towards the airplane, right? And if you're flying like this, the air is moving towards you, isn't it? So the wings are in such a shape, in such an angle, that the air actually moves this way, hits the wings, and turn a little bit to the bottom. Okay? So the air is turned a little bit to the bottom. So which means there are certain air particles that are pushed downwards. So if you push enough particles downwards, you will keep yourself up. Okay? And that's really how airplanes fly. The airplane is pushing down air using the wings. Now, how is this possible? How can you push down air? Now, this is kind of how it works. This is what we call an airfoil. Okay? It is a cross-section of the wing. All right? So if you blow air from one direction, you see that the air slowly rotates a little bit towards the bottom. It's not a big turn, but it's a subtle turn, right? So that creates this turn of the air. You push down air, you keep yourself up. Of course, this is very subtle, which means you need to go really fast and push down a lot of air in order to stay up in the air. Okay? And this is kind of the basic principle of flying. It is still conservation of momentum. Okay? It is still Newton's third law, where you have action and reaction. This is maybe a better picture. Look at this. Let's say you have an airfoil section like this. The air is pretty much flying, is going like this, the air particles. If you give it a little bit of an angle, you see that you're turning this wing. If you turn too much, you will get these wakes and turbulence and this what we call separation of the air, which is not a good thing, I will tell you in a minute. But you see that the more you turn, the more you're turning this thing downwards. And the more you stay up. If you would plot a box around this, and you would look at the vectors of the air, one is moving this way, one is moving that way, you would see there's a net flow going this way, which we call the downwash. And as much as you push down, that much you will push yourself up. Okay? Does that make sense? Yes or no? Good. So, let me switch quickly to my projector here, because I have a few questions for you. So here is what a typical airfoil cross-section looks like this. Okay? And what we do is we blow air towards it. Well, in flight, we really don't blow air towards it. We just go towards the air, right? And it feels like the air is coming towards us. So this is similar of me standing here and someone's blowing air to me, right? You could have an airplane sitting somewhere and blowing air, or you could have the air still and the airplane moving this way. You would still have that air coming towards you. It would be the same, right? So either this airplane is moving and therefore you have an airflow towards you, or you stay where you are and the air is blowing towards you. It's the same thing. Okay? So what happens to these air particles is that the air particles come here, and this is in such a shape that it will take this air and move it curve it a little bit downward like this. Okay? So if you look at each of these particles, each of these, we call these streamlines. Okay? Streamline. Look at the streamlines. Here, if you would plot a vector, this would look like, this would be a real velocity vector. The velocity vector has now two components here. See, it will have one component going in this direction, and there will be a component that will go in that direction. And that component here, all right, and that will be together, it would give you this, right? So these components we call the downwash. They will try to, the downwash will allow you to stay up in the air. This is not very different from a helicopter, where the helicopter is pushing down air, and you stay up in the air. Or this is not very different from a balloon. Have you ever done this? I'm sure you have done this. You might have a balloon, right? And it has air in it, right? And if you let the air loose, the balloon will just fly away, right? So you push down air, you go. Push down air, you fly. You push down air, you fly. In an airplane, you don't see this very clearly. When you look at an airplane flying, you don't see it very clearly. But this is a very subtle thing where you see that you're pushing down air. Okay? Now, let me put it in a more extreme fashion. Let's say I don't have an airfoil, like on an airplane, but I have, let's say, a plate. Okay? This is a plate. So it would be more like this. Okay, it's a plate. So if you blow air onto the plate, do you think we are pushing down any air? No. Will this plate float or fly? No. You just put it there, you blow air, nothing will happen, right? Now put this plate on an angle. What's going to happen now? What's going to happen now? Well, the air will bounce on this plate, probably change direction, hopefully, right? There will be another one. Bounce on the plate, change direction. Bounce on the blade, change direction. Bounce on the blade, change direction. I mean the air particles. Okay, we call this V infinity, the velocity of the air. It will bounce on the plate, change direction. Bounce on the plate, change direction. On the top, this will probably be moving like this. There might be some air particles coming closer to the plate, and you would have this, right? So, a few things happen here. One, first of all, these air particles hit the plate, change direction, right? And therefore, there is a downwash now, and therefore the plate would be going up. Is that meaningful? Just like on a wing. But on the other hand, there's another thing happening here, if you want to explain it in a different way. Every time I hit the plate with a particle, it's hitting it on an angle. See? If this is the plate, and you're hitting this with this vector, right? You're hitting this in two ways, right? You have a normal force that will go in this direction, and this normal force will have two components. One is in this direction, and one is in this direction. And this would be your normal force when you hit this. So there will be always a component that will try to push you up, right? So look at the ones on the top. The top particles, they are just moving about the plate, or they come close to the plate. The ones on the bottom, they try to push the plate. They just hit the plate. And here you might also claim, like someone said, there's higher pressure on the bottom, higher air pressure on the bottom, just because it is hitting the bottom of the plate. And because they are not hitting the plate, you will have low air pressure at the top. Does that make sense? So you hit at the bottom, don't hit at the top, more pressure at the bottom, low pressure at the top, you will go up. So why do you have that high pressure? Because it's hitting it. What happens when you hit it? Well, they will change direction, the particles, and will go down. And because they go down, they have a downwash. So the downwash is a reason. These are all the same things. You can explain this with action and reaction, Newton's third law. You can explain this with conservation of momentum. There is this component that pushes you downward, therefore you're pushing yourself up. You might explain it with high and low pressure. Because you're hitting this, you have high pressure here and low pressure at the top. And therefore, because you have high pressure over here, this plate wants to go up. Does that make sense? All right. Let me plot this one more time. Plate. Air blowing, V infinity. Okay. If this angle is here 0, and this angle I shall call alpha. Okay? If alpha is 0, nothing will happen. You will not get this we call a lift force. We will not get a lift force that will push you up. If alpha is at a certain angle, then you will start seeing that hitting and going up, hitting and going up, right? Well, if these particles hit this plate, you can really divide this into two forces. One is the one that is pushing you upward because of the downwash, and one that is pushing you backwards. Okay? Because it is, this air force, this air will also push the plate backwards. You see? Not only up, but also backwards. Now, these two forces have a name. This one we call the lift force, and this one we call the drag. Okay? So you can have this experiment maybe next time when you are at the pool or at the seaside. I don't know if you have done this as a kid. When you have your hands straight like this and you turn your arms, it's easy to turn. Put your hands at an angle, it will be difficult to turn, right? It's that drag force. Because the air will cause resistance now. In an extreme case, if you make it like this, okay, let's look at an extreme case where the plate is 90 degrees. And you push down like this. That's an extreme case. What are you going to get? You're going to get a lot of drag and virtually no lift, right? And the other extreme was actually when the plate was parallel. And you have air blowing towards the plate. You would get no lift and no drag at all. And if you're at a certain angle, let me put it this way, if you have it in a certain angle, you would get both lift and both drag. Another experiment you can do is when you drive a car, or maybe not if you drive, but better somebody else. Open the window, put out your hand, be careful, very carefully, make sure there's no other car, okay? And put your hands at 0 angle. You'll see the air will just blow towards your hand. Give it a little bit of an angle. You will see that your arm is trying to go up, but also a little bit backwards. Okay? Your arm will try to do that. A little bit up, a little bit backwards. Try it next time. Okay? It's the resistance. Two things happen. If you had, one is, because you have an angle, the air particles will reach your hand, change direction, and therefore push you up. At the same time, it will push you backwards. It will have both a lift and a drag. Okay? If you would have a larger plate on your hand and you would do this, it would be quite dangerous in a car, even at low speeds. Okay? Because if you do this, then there would be a lot of force coming towards your hand if you had a plate on your hand. Okay? You would have lift and you would have drag. Okay? So, make this a little bit now nicer, and instead of this plate, you could use a nice aerodynamic shape, something like that. Okay? And now blow air, and the air will just nicely move like this. Okay? And then you will have a nice lift force, and hopefully not much drag. Okay? And in a real airplane, this would be the wing. Okay? And if you connect this to your fuselage, we call it a fuselage, where people sit, the main body of the airplane, then you could actually, using this lift force, you could actually fly. Okay? You push yourself down the air. Okay? So, any questions? Does this make sense? Is it meaningful? Okay? Now you'll be able to explain this to your mother. If she asks, how is it, or your father, how do airplanes fly? You'll be, of course I know. You're pushing down air. There's lift and drag. Understand that, right? Okay. All right. Let's look at this picture. Which one do you prefer? You want to have a lot of lift on an airplane or a lot of drag? You want a lot of lift, right? You want to go up in the air. You want to create a lot of lift. How about drag? We want to have it little, right? Because this is pushing us backwards. The airplane wants to go forward, not backwards. But this is pushing you backwards, right? The drag. So you don't want to have much drag. But can you have lift without drag in this picture? Not really, because every time you're hitting this, it will push you backwards a little bit. It's not only that these particles are pushing this backwards, or the plate up there backwards, it's also there's friction here, right? There's a lot of friction that will also create some drag. So this drag has really two sources. One is the fact that the particles hit the plate, or the particles hit this plate at an angle, and it will try to push it backwards. And here it pushes it all the way backwards, right? And it's a similar thing, but very subtle. It's also pushing it backwards. But another reason is also because the surface of a wing has friction. So that will also push you back. But it's not only the friction, it's also the fact that you are at a certain angle and these air particles will hit this airfoil and push you backwards. Right? That's what we call drag. So, in an airplane, who accounts for the drag? I mean, if we had only drag, the airplane would be going backwards because the drag is pushing you backwards, right? So, who is pulling me forward? The engines. We need engines to overcome the drag, right? So if I have engines, if I overcome the drag and I push myself forward, only then I will have V infinity. And because of that V infinity, I will go down and I will create lift. So without this air, I have nothing to push downwards, and therefore I will not go up. Now here's the question. If I would be in space and there's no atmosphere, there's no wind, no air, can I fly with this principle? Of course not. There's nothing to push down. You see? So, therefore, in an airplane, I don't like drag that much. Because more drag means more engine power. More engine power means more fuel. More fuel means more money. Okay? So what do you want? You want an airplane that has little drag and a lot of lift. In aerospace, we call this lift to drag ratio, a very important ratio that shows us the efficiency of these wings. So I will ask someone who designs an airplane or a wing or an airfoil even, what's the lift to drag ratio? If they tell me a good number, a large number, I will say, oh, that's good, because you have made such a beautiful shape. The drag is low, the lift is high. If you have a plate like this, the lift-to-drag ratio is not very good. It creates a lot of drag, some lift, but not enough. So the question is, why are we using airfoils like this instead of plates like this? The reason is simple. The lift-to-drag ratio of this geometry is a lot better than a plate. The cross-section of a wing looks like this because the lift-to-drag ratio is quite good. That's really the reason why we are using this particular shape. So how did we come to this point? How did we come to this point? How do we know that that lift is better than the lift-to-drag ratio of that airfoil is better than the plate? Well, turns out in history, humans have tried a lot of different airfoils. Okay? The airfoil, this is a picture of the airfoil of 1908 of the Wright brothers. Curved wings and airfoils are older than Wright brothers. A lot of scientists have tried this. Different airfoils, different wing shapes. But look at this, 1908, thin airfoils. You go in history, 1909, 1919, 1912, 1919, you see it's evolving into these shapes. We call these airfoils, the cross sections. 1919, 1926, 39, 35, they look like modern airfoils. If you look today at a modern airfoil that's designed today, it will look not very, very different from these ones. They will be, of course, a little bit more efficient. But we, as in the aerospace community, we have converged sort of to this shape. And the reason is really the lift-to-drag ratio is much better. It's getting better and better. Okay? So these are the airfoils that we're using on wings. Okay? Someone had that question a minute ago. How does the rotor push down air? Well, each of these blades that you see, actually, if you take a cross-section of the blade, it also looks like an airfoil. So if you turn the blade like this, just like the wing I just explained to you, at a certain angle, it takes the air, rotates it, and pushes it down. So instead of going forward like a wing, it rotates the wing and does the same job, actually. Takes the air, pushes it down. We call it the downwash. Okay? It's the same principle. And because these are, in fact, I mean, they look like blades and they look very thin on this picture, in reality, they are not really that thin. Okay? They are like this much. We call them rotating wings. Sometimes we call it rotary wing airplanes. Instead of saying helicopters, we say rotary wing aircraft. It's wings that are rotating. It's the same principle. Okay? Any questions? Yes, sir.
They don't have engines like placed sides like an airplane, so how
Yeah.
do they go?
Yeah. This one? Yeah. Well, we will talk about helicopters in the next hours, and we will also talk about engines. These blades, they have the power to change their angles. So what they do is they change the angle in the front, and when they go backwards, they change the angle again. So somewhat, they are designed to push down more air at the back and less air at the front so that the whole thing is tipping forward. Okay? So when the helicopter rotor rotates, it doesn't rotate at a constant angle. It has low angle here, high angle on the back. So high angle means more lift, and therefore you turn, and then you go forward. The engines are used to turn the rotors, that's it. The engines are not used to push the helicopter forward. It's only used to rotate the blades. Any other questions? I will talk a little bit more about helicopters a bit later. Okay. Here's another question to think about. All right, let's summarize this real fast. So this is an airfoil. And let's say this is an airfoil can be symmetric or not unsymmetric. Now it is not symmetric, but it could also be a symmetric airfoil. In fact, the airfoil might look like this, like totally symmetric. Symmetric. And if you have a symmetric airfoil, then this is how air would fly around it. It would be symmetric at the top, symmetric at the bottom. Would this create any lift? No, right? Because it is the same on the top and the bottom. Nothing is curved towards the ground. You don't have any downwash. The pressure difference is the same, so it will be doing this. So no lift for this one, no lift. Do you think this would create any drag? Why? Well, first of all, there's friction, right? And because of the friction, there must be some drag. So there's some drag in this direction. Drag due to friction. Okay? So let me give this symmetric airfoil a certain angle. I'm going to make this angle quite large to illustrate it a little better. So this is supposed to be a symmetric airfoil. Okay, it's symmetric. Blow air. And the air will do this. It will hit this and go this way. Hit it, go this way. And this one probably also curve and do this. Okay? And because you have a downwash and so on and so forth, you will have a lift now, because what I explained, so you will have a lift. And you will have obviously some drag. And the cause of the drag is not only due to friction, air friction, right? But also because it is hitting this thing, right? It's hitting these air particles, hit this airfoil in this direction. So it is kind of hitting it. And because it's hitting, it's creating lift, but also drag. So we call this, the drag is due to lift. If there was no lift, there wouldn't be drag, right? You're pushing it back upwards, but also backwards. So it's drag due to lift. So you have this drag as well. There's one more thing. I keep saying I'm giving this a certain angle. I think I mentioned this already. We call this alpha, this angle. And alpha is known as the angle of attack. Okay? So if you look at this picture up here, the angle of attack was equal to 0. Right? No angle of attack. This one here does have an angle of attack. Therefore, it has lift and this is drag. Here it has only drag because of lift. Here because it has drag because of air friction and due to lift. Does that make sense? All right. So here's my question then. Let's say I have an airplane, I design an airplane, and my airplane is 100 tons. 100 tons. How much lift do I need to go up? It's very simple. More than 100 tons equivalent, right? Tons is really mass. So it would be this many newtons, right? 10,000 newtons, I believe, approximately. right? 10,000 newtons. Okay. So you need 10,000 newtons of lift. How can we create more lift? What should I do on my wing to have more lift? Well, I need to push down a lot of air particles, right? Okay. So I tell you the first one. The bigger my wing, the more air I will push down. Is that right? If I have a wing like this, it's only this much. If I have a huge wing, there will be a lot of air coming down. So the size of the wing will tell me how much air I will push down and therefore how much air I can go up. So size of the wing, that's the first one. What else?
Engine capacity and power.
So what about power? What happens when you have power?
It pushes.
What?
Air increases velocity.
Increase velocity. I don't care about the power. If you increase the velocity here, then a lot more air particles will come towards me. I will push down more air particles than usual, and therefore I will create more lift. So increase the velocity, right? V infinity. Sorry. Is that? Yeah. Yes, please. Increase the angle of attack. Obviously, if you increase the angle of attack, more air will be turned this way, and therefore you will go up. So let me write this down so we don't forget. 1. How to get more wing? How to get more lift? How to get more lift? Okay. 1. Increase size of wing. 2. Increase air velocity. 3. Increase angle of attack. Anything else? What else can we do?
Minimize the weight of the aircraft.
No, the weight is fixed.
Changing the airfoil shape.
Changing the airfoil's shape. Make it a nicer airfoil so that it creates more lift and less drag, right? The L over D, remember? So if you have a better shape, it will give you more lift. Okay, change the shape of the wing. 4, change the shape of the airfoil, let me call it, okay? What else? Yeah. How would that change? How would that help? Change the material of the wing. How would that help? Why the material? The airflow doesn't care if this is carbon or if it's metal or the air particles don't know what this is. They will just go and push it downwards, right? So the material of this doesn't matter.
Maybe we can create shapes.
Yeah, okay. I already wrote that down. If you have different shapes on the wing.
Like ways to go.
Of course, yeah. That includes everything. You can do any shape you want. It doesn't have to look like this. You can make anything you want. You can make this, put little things in there, whatever you want. It's all included in the shape. Okay? There's one more thing you can change. You can go closer to the floor and you have something called a ground effect. But let's take it to the side. Let's say we are up in the air. We are pretty high up. What else?
We would decrease the friction by changing the material.
You can decrease the friction of this thing, right? You mean? So the drag will be less. I'm not sure how much it will help the lift though. The air friction will change. You will still have drag due to lift. And the lift will still be there. So it's not helping the lift too much. It will help the drag, but not the lift. One more thing. What about the air density? See, we have the infinity below. I mean, you need a lot of air particles to push down. If the air particles are less in the air, right, it will create less lift because there are less particles coming this way. But imagine there's a lot of air, So with the same speed, same shape, same angle of attack, you will create more lift if you have more air, right? Where is this happening? I mean, is there a change in the air in terms of density? Of course there is. On the ground there is a lot of air. If you go up, the air becomes less and less, right? So the density becomes less when you go up, right? So when you fly at high altitudes, it means you need to go either faster or have more angle of attack, right? Or change the shape of your wing. You choose, right? Is that good? So the fourth one, or what do we have now? The fifth one is air density. Okay? These are the ones that affect the lift. Now, believe it or not, this is how we write the lift formula. The size of the wing, call it S. Surface area. Okay, let's call it the surface area of the wing. Air velocity, call it V. Angle of attack, call it alpha. Shape of the airfoil, well, it's a parameter called CL that represents the shape of the airfoil. I will tell you a little bit more about this. Air density, rho. Okay. Do you want me to write the lift formula? Okay, and this is maybe the first equation you learn in aerospace, but never forget it as long as you're in this business, okay? 1/2 rho V square CL alpha times S. Okay? Let's call this CL alpha here. I will tell you what this means in a second. So it's not really CL. All right? Density. Square of the velocity. So the velocity makes a big difference. If you go twice the speed, you will get 4 times the lift. CL alpha is a constant. Okay? Alpha, angle of attack, S, surface of airplane, of the wing. So if you want to go faster, if you get more lift, you need to increase one of these. Okay? There's no other way. Here's the interesting part. The drag is not any different. The drag formula is also like that. 1/2 rho V square CD alpha times S. And plus you might have some of the friction. So if you look at this, increase rho, increase velocity, increase CD alpha S, you all increase the drag as well. So the more lift, you always pay with drag. Right? So if you have a heavier airplane, you need more lift, what do? You need more drag. You will have more drag. As a result, you put more engines, bigger engines, and therefore more thrust and more fuel. Okay? So you always wonder how lift is correlated to your engine power. Well, it's correlated through these equations. Increase these things, this will also increase. Okay? Now, I have written this one here. In this one. What they mean is this. CL alpha, we can plot a curve CL versus alpha for an airfoil. Okay? So let's say you have a symmetric airfoil. If it's a symmetric airfoil, then at 0 alpha, you get 0 lift, right? We looked at that. If it's a symmetric airfoil, like this, 0 CL at 0 alpha, so you are here. If you increase alpha, CL will slowly increase, so you will get something like that. Okay? You cannot increase it too much, because after a while, what happens is if you have a really large CL, let me put it here. If you have a really large alpha, you have a large alpha, what happens is when the air is moved here, this air will not stay here anymore and it will start separating. And you will get these wakes and turbulence and stuff like that. Okay? And suddenly you have a lot of pressure on the top as well. Okay? If this happens, if the flow starts separating from the airfoil, we call it the stall region. And the lift will start dropping and drag will start increasing a lot. So this is CL and this is alpha. So what's going to happen is the CL alpha will go up and up. As alpha increases, CL will increase, and after a while it will start dropping. And this is where you have what we call the stall region. Okay? Now, coming back to my formula, you might ask me, what is CL alpha then? Well, CL alpha is the slope. Okay? Is the slope. So it is basically del CL, del alpha. So that's what we call CL alpha. Okay? So which means if you calculate del CL, del alpha, times alpha, what do you get? You find CL. Right? That's what we call is the slope. So here in this formula, CL alpha times alpha is really CL. Okay? It's the same thing over here. So this is what we call stall. Unfortunately, this CL will slowly drop as stall goes down. Okay? So this is your lift and drag formula, and this is what helps you. All right? Good. Let's think of an airplane that is quite heavy that day. Okay? Lots of baggages and lots of passengers. It's full, lots of fuel in it too. It's very heavy. What can it do to take off from the ground? First of all, you need velocity, right? Okay. So you need to increase your velocity. But unfortunately, the runway is a certain length, right? And the runway is not infinitely long. This is your runway, and that's your airplane. Okay? So you have this much of time to go to a certain velocity until you take off, right? And if you're really heavy, you need a long runway, obviously. Okay? But this length should be enough for you to take off. If this doesn't work, what else can you do? If the velocity is not enough, what else can you do?
We can use wind to assist engines.
How?
So pushing air.
How do you assist the engines? I don't understand.
We can go against the wind,
Mhm.
so it goes this wind.
We
And
go-
engines are also pushing.
We go towards the air, you mean? What do you mean?
We go against wind.
We are if there's a wind, but if there's no wind that day, what do you do? I mean, here's what he says. Here's what he says. Let's say you have an airplane that's sitting on the ground. Right? Sitting on the ground. And you want to take off. And let's say on that day there's a lot of wind. The wind is blowing from the back or from the front. Which one would you prefer if you want to take off fast? You want the wind coming from the front or coming from the back? From the front, right? So that you stay there, the air is flowing towards you, you just have to make your wings a little at a certain angle and immediately you will push down air and you will go up. In fact, if you look at these pictures here, look at these pictures, if the airplane was not moving forward, you could just stay there, and if someone would blow air to me, all I need to do is give it a little bit of an angle of attack, and you will go up, right? So if you have air blowing from the front, if there's a wind, it would be really nice. So then I don't have to increase my velocity, my ground velocity, as much. So let's say if I increase my ground velocity to 250 kilometers per hour, and if there's no wind, I will still get 250 kilometers per hour from the front. But if there was a wind, an extra 30 kilometers per hour, the wings would feel 280 kilometers per hour. So that would help me. Okay? So what you do up here is that you try to accelerate yourself to a certain velocity that is good enough for you to take off. One other thing you can do is here, if you look at this, you can play with rho. I mean, that is the air density, whatever it is. Velocity is a certain, you can go to a certain velocity. You can't really change your shape too much, I mean your wing shape. But what you can do is you can increase the surface of the wing a little bit sometimes. You know, airplanes have flaps. Did you see those flaps that go sometimes up like this and go down like that? So if you make it a little like that, if you take it out a little bit, you can do two things. You increase the surface of the wing, but at the same time, you increase the shape a little bit too, so that it pushes down more air. So you play with these two. But whenever you play with these two, you also play with these, and therefore your drag will also be larger. Nevertheless, as soon as you reach a certain velocity, all you do is move the nose up a little bit. You do that with the ailerons at the back. You push your nose up, and then you have a lot of angle of attack, and suddenly you start going up. Okay? Now, when you're in the air, when you're up in the air, this is the situation. Let's say this is the air. This is your airplane. You're up in the air. Okay? You have V infinity blowing towards you. Okay? And therefore, and these are all at a certain angle. Okay? There's a little bit of an angle of attack. Usually we don't see it, but if you're in an airplane next time, look at the nose of the airplane, you will see a subtle angle. The airplane will not be exactly straight. It will have a little bit of an angle. Not much. We are talking 10 degrees, 8 degrees, 10 degrees, 12 degrees, something like that. Okay? Not much, but it will be there. There will be some angle of attack. That will create you lift. And it will create drag. The lift is, of course, balanced by what? By the weight. The airplane has a certain weight. So these two will try to balance themselves. The drag will be balanced by thrust. And that comes from the engine. So that will be the thrust. And that's your thrust. So thrust will balance drag, lift will balance weight, and we are all happy flying in the air. Okay? Now, here's something. When you go up in height, what's the altitude typical airplanes fly, like passenger airplanes?
9,000 feet. A meter.
Meters. So it's about 30,000 feet. It's about 10 kilometers, right? 10 kilometers. So let's say you're flying at 30,000 feet. Well, what happens is, the most significant thing is that rho goes down. The density is going down, right? Therefore, you need to go faster, or you need more angle of attack, right? Either one of those, in order to go up there. What happens is when you're going up in the air, remember when you are taking off, how fast do you think these airplanes accelerate, or to what velocity do they accelerate when they want to take off in this short distance? 200 kilometers per hour? I mean, when you take off, what is your velocity at that point? Well, let's say it's a passenger airplane like a 737 or Airbus 120 something typical passenger airplane? Well, it's about 200, 250 kilometers per hour, sometimes 300, but it's about 250 kilometers per hour. It's not very fast. I mean, faster than your car, probably, but it's still 200 kilometers per hour. Okay? Here, when you take off. When you go up here, what's your velocity here when you're up in the air for a passenger airplane? It's approximately 900 kilometers per hour when you're up in the air. It's approximately 4 times than your takeoff velocity or your landing velocity. 4 times. What happens if you have 4 times the speed? How much more will be the lift? 16 times more. Therefore, you get a lot of lift because of this velocity. And this rho, it can decrease. Doesn't matter, because you have so much velocity. And therefore, the angle of attack, when you're flying up there, is actually less than when you're taking off. When you're taking off, you need a lot of angle of attack because the velocity is so low. When you go up, it's the opposite. What happens when you're landing? What happens when you're landing? Do you think the lift must be a lot less than the weight when you're landing? Yes or no? When you're landing, should the lift be much less than the weight? Or do you need lift when you're landing? Of course. When you don't have lift, what's going to happen is you're going to fall down like a stone. You don't want that, right? If you look at airplanes, they go at a very nice velocity like that. So if you look at it, actually, the velocity is sort of constant. I mean, you're going downwards, but the velocity vector is constant. If the velocity vector is constant, it means acceleration is equal to 0, right? If velocity is constant, acceleration is 0, which means there is no net force. F equals ma, right? Acceleration means force. So if there's no net acceleration, there's no net force, which means this is still kind of the picture that you would see where the forces are sort of in a balance when you're landing. So you still need similar lift when you're landing. It's just maybe a little bit less so that you slow down. I mean, you go downwards at the beginning. But then after you reach the equilibrium, lift is equal to weight still. Okay? So here's the question then. What's your landing speed?
200.
Similar to takeoff, so it's 200, 250 kilometers per hour is the landing speed. Okay? Why can't you land at 900 kilometers per hour?
The highway.
You would need so much space to slow down that would I don't think an airport would be enough. Right? You need to slow down and land. Okay? And you're slowing down to 200, 250 kilometers per hour, just like in takeoff. So what do you need now? You need a lot of angle of attack, because the velocity is now a lot less. A lot of angle of attack. A lot of surface area, therefore you have flaps. Right? And you need to change your shape. You know, the flaps go a little bit down. The airfoil flaps look like this. See, when you're flying up in the air, this is your wing, right? When you're landing, this piece actually bends and goes down like that. Okay? So while the airfoils were doing this, now it's trying to do that. Okay? It makes it both bigger, increases the surface, and also the shape. So what you're changing is you're changing CL alpha, but you're also changing the surface area. Okay? And this is small CL alpha and small surface area. So this is what you see on those wings when you're landing. Okay? Sometimes you see wings that they have a huge flap. They almost go like that. Did you see that when you're landing? And on top of this, the airplane actually makes an angle of attack like that. So you have this high angle of attack, and you have this new shape, and you have a bigger wing, and you're trying to land with it. Okay? So that way you're trying to increase your lift because your velocity is going down almost 4 times than your cruise speed at the top. So if you think about it, at the top, the airplane is kind of flying straight. Sorry. It is kind of flying straight. The airplane at the top is kind of flying straight, right? Doesn't have much angle of attack when you're up there. Because you're flying at 900 kilometers per hour, you don't need much angle of attack. But when you're landing, the airplane is landing like that. Large angle of attack, big wings. Look at the birds do the same thing when they're landing. They have these big wings and they do this when they're landing, right? When you're up in the air, they're flying a lot nicer. They don't use much power, but they use a lot of power when they're landing, when they want to slow down, okay? Same thing over here. So when you're landing and you have this low velocity, okay, what's going to happen? Lots of angle of attack, lots of lift, this shape. But what's happening, unfortunately, also is once you do this to your wing, yes, the lift will go lift will go up, but so will be the drag. So the lift to drag for something like this is pretty bad, okay? It's a lot better when you do this. This is a lot nicer. This will give you a lot of drag. It will give you also lift, but also a lot of drag. And therefore, because you have a lot of drag during landing, you have seen a lot of airplanes probably that are trying to land, like that, with a high angle of attack, with wings, where the wings the flaps are on, and you have a high angle of attack, okay? And you're trying to land. The L over D here is not very good, which means you have a lot of drag pushing you backwards. What do? Well, you need a lot of power to overcome this. In fact, you need a lot of engine power to overcome this drag because you're slowing down, because you still need that lift at that low speed. And oftentimes the power you need during landing is a lot higher during this nice cruise speed where your speed is 900 kilometers per hour. Okay. Many airplanes, of course, spend a lot of time at that velocity, at that altitude, at that flight condition. So we try to optimize everything for that flight condition to be optimal here. And during takeoff and landing, we just try to do our best. Slow down as much as you can. Put your nose up. Full power. Can we slow down more? Can we slow down more? Right? That's how we move. So this is the L over D situation. Okay? Any questions? Yes?
How to calculate CL and CD?
How do you calculate this CL and CD? So I told you that's a good question because it looks like a mystery, right? This is your CL and this is your alpha. And if it's not a symmetric airfoil, in fact, it will look like this. Okay, and this is kind of your stall speed. The stall speed is about, it's not much. It's usually less than 20 degrees. Okay, this is stall, and this is usually less than 20 degrees. So this CL alpha, how do you calculate this curve for an airfoil like this? Well, there are two ways. One is you take it and put it into a wind tunnel, what we call a wind tunnel. A wind tunnel is basically a controlled area that we have in the lab. We have a few wind tunnels over here as well. So it's like a tunnel, okay? You put a wing into that wind tunnel, or a two-dimensional, let's say. You can't really put a two-dimensional plate here, but you just approximate it with a wing, okay? Put it like this. We actually have fans over here and the fan is blowing air. Okay? At a certain velocity. And then we have a little mechanism here that measures the forces at this point. Okay? You can measure the force at this point with some pressure sensors. And then you measure this, and you measure this, and you plot it. You give it a certain angle of attack. For each angle of attack, you calculate a new lift. Okay? And then you calculate this plot. So how do you do it? Well, if you look at our formula, CL, I'm sorry. Where is it? I just had it here. If you look at this formula, CL is equal to lift over, CL is equal to lift over 1 over 2 rho v squared s. Isn't it? So all you need to do is actually calculate the lift in the wind tunnel for a certain alpha, right? And then divide it by 1 over 2 rho v squared of v infinity times the surface. And then you find CL for that particular alpha. Do it for different alphas, find different CLs, and plot it. And then you have this curve. And then you can look at this and find CL alpha. Make sense? It's easier explained than done. Okay? You need nice airflow everywhere and nice precise measurements to do this precisely. Another way of doing this is to do this in the computer. Of course, we have a lot of simulations of the airflow around a body. So we can actually simulate this airflow in this computer. And then we do the same thing on the computer and still generate a CL alpha. We call it computational fluid dynamics, CFD. That is used to find these CLs and CDs for these shapes. In fact, because you do it on a computer, now you can optimize the L over D and try different shapes in the computer and find the best shape that will give you a certain lift and a certain drag at a certain velocity and a certain altitude. Remember I told you we're trying to optimize the flight for this situation, 900 kilometers per hour, 30,000 feet. We are trying to optimize it for this. Because this corresponds to a certain air density, so the question is, what is the air density that I need? What is the best shape that will give me the best L over D at that velocity, at that altitude? Now play with the airfoil, make it longer, smaller, fat, thin, whatever you want, and try to obtain the best L over D. In other words, try to obtain the best shape that will give you the best L over D.
Which surface do we mean?
If it's an airplane, we mean the surface of the wing. Okay? We mean the surface of the wing. So basically, the bigger your wing, the more you have lift.
The landing, why does stair?
I'm sorry, just 1 second. If we mean, if it's a two-dimensional airfoil, which in real life doesn't mean anything, right? A two-dimensional airfoil doesn't create lift. Two-dimensional means it's look like this. If you look from the front, it's a thin plate, right? It's nothing. So, but theoretically, an airfoil would create lift, even though it's two-dimensional. At that time, we calculated with the chord, the length of the airfoil.
During the landing, why does the stair part of the airplane touch the runway first?
The which part?
The stair.
The what?
The end of the airplane.
The end, you mean? Yeah, because it needs a large angle of attack to land. You cannot land like this. It needs a large angle of attack to land because the velocity is low. You increase the angle of attack, you increase the surface of the wing, and therefore you have this large angle of attack while you're landing. So naturally you're touching with the back first. You cannot land like this. If you land like this, two things can happen. Either you don't have lift and you fall down like a stone, or you have lift but you're very fast and the runway will not be enough. So you slow down, large angle of attack, naturally you touch with the back first. Any other questions? Okay, so let me continue with my presentation. Do you have any questions? So this is what I called, this is where stall starts, where you have where you have separation, okay? Airfoils, I told you, many different shapes of airfoils. This is an airplane during landing. Look what I just mentioned. You have this angle of attack, you see? You're going at a certain angle, and the wings are as much as possible. Look at this angle. This angle is not that much, all right? But still a lot, because this happens at around 20 degrees, less than 20 degrees. For some airfoils, it's even 16, 17 degrees. You start seeing separation, what we call stall. So it can be very, very high. This can be very large, okay? Pilots don't like stall, because when you stall the wings, separation, you start falling down very badly. Don't have lift, right? And a lot of drag. The bad thing is this will create a lot of drag as well. So what happens if you have a lot of drag suddenly on an airplane? It will push you backwards. The engines will not be enough. It will push you backwards. If you push yourself backwards, you slow down. What happens if you slow down? Lift will go down even further. The more the lift will go down, the faster you fall. Oftentimes the drag will become large. So it's like a cycle, right? You have too much angle, too much drag, you slow down, lift becomes less, right? And because you're falling down, you lose control very quickly. So airplanes don't like to go into stall. Nobody likes stall.
Is the wing designed like the range of the angle of attack is just until 20 or
No.
it can be?
No, the pilot can actually put the whole nose up as much as it wants. And if he's not careful, he might actually stall the airplane. It's not only the wings. See, you cannot move the wings independently. The whole body is moving. Okay? So the airplane can actually do has this whole region of movement.
Why gives the pilots a chance to make a mistake?
It's not a mistake. It's the pilot. I mean, now listen. This range of movement you need for different reasons. It's not only the stall. For example, you have probably seen airplanes doing this, loops. The angle of attack is the angle between the body and the air velocity. If the airplane is flying like this is your air velocity, so this is your angle of attack, right? So let's say the airplane is doing this. Then this is your angle of attack and you're stalling. But let's think of an airplane that is doing that. So the air velocity, the relative air velocity, here it's like that. But if you're doing this, if the airplane goes up like this, where is the airflow? It's here. Right? If you're going up like this, the airflow is not here. If the airplane is going up like that. The relative air is here. What's the angle of attack? 0. It's like that. Going like this or going like that is the same. So the angle of attack is actually small. So if the airplane is in this picture like that, it doesn't mean that the angle of attack is large. You see? So the airplane might be doing this with very small angles of attack. The angle of attack is coming up when you're doing this. That's stalling. So you might want to give the pilot this movement, but you don't want to let him do this. And there are systems in the airplane that sometimes prevent the airplane from going into stall. so it will not allow the pilot to do certain things. But this is a two-way street, because you want to give the pilot the freedom, because there might be an emergency situation where he needs to do that to save the airplane, right? But you take away everything and say, the pilot, you can't do this, you can't do that, and then there might be situations where he needs that authority, okay? So it's always a two-way street. In fact, it's a different in philosophy. You go to Airbus, it doesn't give much authority to the pilot. You go to Boeing, they want to give more authority to the pilot. It's a different way of thinking. And then you ask the pilots, which one do you like better? Of course, everyone likes more authority. What if I give you a car that says, you turn this, after a certain time we will not allow you to turn it any further? What are you going to do? Sometimes you have to risk it a little bit, right? Why do I give you the authority to use your steering wheel in the car to kill yourself? Right? It's the same question. So anyway, landing, you need a lot of authority, right? Look at the bird. This is also landing. Does the same thing, you know? A lot of power. Big wings. Large angles of attack. Right? It's a very similar concept. All right. Heavier than air vehicles. Airplanes we call heavier than air. Right? Because if you had a balloon that was lighter than air, you could actually still fly, but it's a different concept. I mean, you know, this thing, let me go backwards. Lighter than air vehicles. This flies too, it's a balloon. What does it do? It has a gas in here that's heavier, that's lighter than the air surrounding, so you have the typical buoyancy force according to Archimedes' principle, and you go up. This is very different from pushing down air and keeping you upwards, right? It's a different concept. You're just lighter than air, therefore you go up. Okay? It's Archimedes' principle. We call it lighter than air vehicles. But this is heavier than air vehicles. So if it's heavier than air, just by sitting here, you will not go up. You need to do something. Yes?
How does a balloon land?
Well, you need to get rid of the light air. Okay? To get rid of the light air. One way or the other. If it's like a hot air balloon, you just cool down the air and it will let you in. Okay. Fixed wing airplanes, we call them fixed wing airplanes. The wings are fixed. Rotary wing airplanes are rotary wings, right? They're rotating wings. All right. So the wing is what we call the wing length we call the span of the wing from one tip to another. Okay. In this direction we call it the chord of the wing, and every wing of course has a thickness. All right. The ratio between the tip, between the chord and the span, that ratio we call the aspect ratio, and the way this looks like, we call it the wing platform. Okay? Now I'm going to tell you a little bit about these things, but we'll do it next week, and we are now out of time, I guess.